Welcome back, Apologia, 8th grade physical science, week 19, day 3, textbook pages 323 to 328, notebook pages 266 through 272. Hearing. The bowl in part 2 of experiment 9.1 that we are actually going to do in class is actually a pretty good illustration of the sound sensing mechanism in your ears. Each of your ears has a thin layer of tissue called the tympanic membrane that is tightly stretched across the ear canal. This structure is also called the eardrum. When sound waves enter your ear, they cause the tympanic membrane to start vibrating, much like the sound waves in the experiment caused the plastic wrap to vibrate. Those vibrations are then transmitted to your brain, and your brain interprets them as sound. So figure 915 helps us understand that. So the outer ear gathers and focuses the sound waves, so the sound energy, and it brings it into the middle ear. Then the middle ear receives and amplifies the vibrations. Nerve endings in the inner ear sense the vibrations and send signals to the brain. When sound waves reach the inner ear, the inner part of the ear, they cause the tympanic membrane to oscillate. Tiny bones called ossicles transfer those oscillations to the cochlea, which converts them into electrical signals that are sent to the brain through the auditory nerve. Your brain interprets the electrical signals as sound. We will be doing the You Do Science feeling sound waves in class. Then we will also be moving on to experiment 9.2, the speed of sound, which we will also be doing in class. All right. What is the correct answer for the speed of sound? Well, it really depends on the temperature. The speed of sound in air is given by the following equation. So we have the speed of sound, V, equaling the quantity 331.5 plus 0.6 times the temperature in meters per second. In this equation, V stands for the speed of sound, while T stands for the temperature. In order for this equation to work, the temperature used must be in units of Celsius. To determine the correct measurement for experiment 9.2, then you would need to know the outside temperature in degrees Celsius. Then you could plug the temperature into the equation, the way I do it in the example below, and determine what the correct answer should be. All right, so example 9.2. If the temperature is 68 degrees Fahrenheit or 20 degrees Celsius, what is the speed of sound? Always step 1, write the list of knowns and unknowns. Remember the temperature must be in Celsius. So we have the temperature of 20 degrees Celsius, and we're trying to find the speed in meters per second. Step 2, what equation will we use? We will use equation 9.2. The speed of sound equals 331.5 plus the quantity of 0.6 times the temperature in meters per second. Step 3 and 4, write out the equation substituting the numbers from step 1 and solve. Remember that in equations like this, you must do the multiplication first. Then, after you multiply, you can add. You may want to write the multiplication part in parentheses to help you remember. All right, so we have V equals 331.5 plus the quantity in parentheses, 0.6 times 20 degrees meters per second. That gives us 343.5 meters per second. That is the correct answer. All right, in your experiment, you probably got an answer between 290 and 400 meters per second. And again, we did not do this yet. The experiment you performed was not all that accurate, however, so do not be concerned about the actual answer you got. One of the more important things to draw from the experiment is that the experience of seeing the cause of sound before hearing the cause itself. And again, we will do that in class. The technique you used in experiment 9.2 can also be used when watching a thunderstorm. If you've ever watched lightning before, you probably have experienced seeing a flash of lightning and then hearing the thunder clap a few moments later. Thunder and lightning are actually formed at the same time. Since we're studying sound in this module, let's talk about the sound of thunder you hear. As the electrical charge of the lightning heats the air around the storm cloud very quickly, the added thermal energy causes the air to quickly expand, and this causes a wave which, when it hits your ears, gets translated into a boom of thunder. If lightning and thunder are created at the same time, the delay you experience between seeing a lightning flash and hearing the thunder is due to the time it takes sound to travel to your ears. Remember, light travels very quickly. The speed of light is so great that the time it takes for light to travel even several miles is simply too small for you to measure. Thus, as far as you're concerned, you see a lightning bolt essentially the same instant it is formed. Sound travels much more slowly. However, as a result, you often do not hear the thunder until much later. All right, example 9.3. A physicist is watching a thunderstorm. She sees a flash of lightning and then hears a thunderclap 2 seconds later. If the air temperature is a cool 15 degrees Celsius, how far away from the physicist was the lightning forming? All right, because light travels so quickly, we can assume that the lightning was formed at the instant at which the physicist sees it. The time delay that the physicist observes then is simply the time it took for the sound to travel from the point at which the lightning was created to the physicist. Okay, first, we need to know the speed of sound, which can be determined using equation 9.2. Once you know the speed, you can use equation 6.1 to find the distance traveled. So this is going to be a two-part problem. Step 1 is always write the list of knowns and unknowns. We know the temperature was 15 degrees Celsius. It took 2 seconds in time. We're trying to solve for the speed and the distance. Step 2, write the equation. The speed equals 331.5 plus 0.6 times the temperature in meters per second. Steps 3 and 4, write the equation substituting the number from step 1. So again, we have 331 plus the quantity 0.6 times 15 degrees Celsius. That gets 340.5 meters per second. Now, step 5, write out the equation for speed. Speed equals the distance over time. So we need to rearrange the equation to solve for the distance. So if we multiply both sides by time, we can have the distance equals the speed times the time. Step 6 and 7, write out the equation substituting the numbers from step 1 and 4 and solve. So D equals the speed, 340.5 meters per second, times 2 seconds. And you get 681 meters. So therefore, the lightning was formed 681 meters from the position of the physicist. Although the way I solve the example is the most accurate way to determine how far a lightning strike is, there is an easy method that gives relatively good results as well. It turns out that thunderstorms usually result when cooled air, called a cold front, moves in under warm air, a warm front. Thunderstorms therefore usually result in cooler temperatures. A good guess for the temperature in a thunderstorm is around 16 degrees Celsius. At that temperature, sound travels at about 341 meters per second. Well, 341 meters is about 1/5 of a mile. In other words, during a thunderstorm, you can estimate the speed of sound to be 1/5 of a mile per second. As a result, for every second of delay between the lightning strike and the thunder, the lightning strike was about 1/5 of a mile away. If you count 2 seconds between a lightning flash and the resulting thunder, then the lightning struck about 2/5 of a mile away. Although you will not be able to use this simple estimation to answer problems, you can use it when you are watching lightning strikes. All right, on your own. What is the speed of sound in air when the temperature is 28 degrees Celsius? Step 1, what are the lists of knowns and unknowns? 28 degrees Celsius, and we're trying to solve the speed. Step 2, write the equation, 331.5 times 0.6 times the temperature in meters per second. Substituting in the temperature and solving for the problem, you get the answer as 348.3 meters per second. On your own, 9.7. During a thunderstorm, the temperature is 18 degrees Celsius. If you see a lightning flash and hear the thunder 1.5 seconds later, how far away did the lightning actually strike? To determine how far away the lightning struck, we will assume that the light from the lightning bolt reaches the physicist's eyes pretty much instantaneously. Thus, the time delay between seeing the lightning and hearing the thunder tells us the distance. First, however, we need to determine how quickly the sound travels. Then once we know the speed, we can determine the distance that the sound travels. Step 1. Write the list of knowns and unknowns. We've done that. The temperature is 18 degrees Celsius. We're trying to solve for the speed. We're trying to solve for the distance. And we know the time was 1.5 seconds. Step 2, write out the equation. V equals 331.5 plus the quantity 0.6 times the temperature. Step 3 and 4, substitute into the equation and solve. Using the 18 degrees Celsius temperature, we get the answer of 342.3 meters per second for the speed. All right, now step 5, write out the equation for speed and rearrange. We've done that earlier. So we know the equation for speed is speed equals distance over time. We rearrange it to find out the distance equals speed times time. Step 6 and 7, write out the equation and substitute. We get 513.45 meters. The lightning, therefore, was formed 513.45 meters from the position of the physicist.